Hi, we are Team AKS and today we are going to talk about our project on designing wireless satellite hub. Our task was to design a wireless satellite hub which would act as an intermediate memory while processing a command for send or request of data from client to the data center in such a way that the total cost of the system is minimum with minimum latency. In order to achieve this, the following memory combinations are used. We Along with this, we have also used two 16-bit buffers in the hub. We have made the following assumptions. We have assumed that the data center has infinite memory, all the clients send and request data sequentially, and the latency is calculated based on these assumptions. We have used FIFO for eviction algorithm. The links between the hub memories are parallel. L1 and L2 is used to store the bytes as mentioned, and L3 is used as a backup memory. The 32-bit command word consists of tag and send request command. Communication between the satellite hub and the data center is considered for communication cost. The tool being used is Model Sim and the programming language is Verilog. The constraints are as follows. No M1 memory is used. One separate M3 memory is used as a backup memory. Single link is used between client and hub, which means two clients cannot communicate at the same time. Execution is done sequentially, and M2 and M3 are used even though they have more latency than M1.
Now let's see why we have chosen this particular design for our system. Here we can see that we have only selected M2 and M3. We have excluded M1 because it is very costly. Here we can see the calculation of the cost of our memories. It comes to $70. The trade-off here is that if you increase the cost, then the latency will decrease, but the cost will be very high. If you decrease the cost, there will be more latency. So we have tried to make a balance between both the constraints and tried to design a memory which has moderate latency but the cost is little less. This is the block diagram of our system. Here we have three memories, that is L1, L2 and L3. L1 memory is dedicated only for 128 or 512 bytes. L2 memory is only dedicated for 1024 bytes. L3 memory can be considered as a backup memory. If L1 gets full, then the next incoming data will be stored in L3. If L2 gets full, the next incoming data will be stored in L3. There is a serial bus between the clients and the hub. This bus is a bidirectional bus. We have a data center which can be connected to the hub using a satellite link. Here we can see the flow of our algorithm. In the start, we will get three inputs from the client. The first one will be the command, the transaction size and the device number. The command will give us the tag and if it is a send or a request. It will check if it is a send or a request. If it is a send, it will check the data size. If it is a 512 or 128 byte data, then it will check for the space availability in L1. If space is available in L1, it will store in L1. If there is no space available in L1, then it will check for space availability in L3. If there is no space available in L3, it will execute the eviction algorithm. If there is space available in L3, it will store in L3. Now let's see if the data size is 1024 bytes. It will check for the space in L2 as L2 is dedicated for 1024 bytes. If there is space in L2, it will store it in L2. If there is no space in L2, it will check for space availability in L3. If there is no space in L3, then it will execute the eviction algorithm. Now let's see if it is a request command. If it is a request command, it will check for the data size again. If it is 128 or 512 bytes, then it will check for the tags or the tag match in L1. If the tag matches, then the data will be given out to the client from L1. If the tag doesn't match, it will check for the data tag in L3. If the tag matches in L3, the data will be given out to client. If the tag doesn't match in L3, then eviction algorithm will be implemented. During this eviction algorithm, data will be taken out from the data center, stored in the hub, and given out to the client. Now, if it is a 1024 byte request, then it will check if the tag match is there in L2. If the tag doesn't match in L2, then it will again check tag match in L3. If in L3 also the tag doesn't match, then it will do the eviction algorithm, in which again the data will be taken out from the data center, stored in the hub, and then given out to the client. If the tag matches in L2, then the data will be directly given out to the client. Now I will explain you how the eviction algorithm works in our system. First, I'll explain you how the data is stored. Whenever there is a send request, then the first data is stored in the first position. After this, the index is incremented and the next incoming data is stored in the second position, and so forth. Now let's see how the eviction works. In case of eviction, whenever the memory is full and a new incoming data comes, we implement a first in first out eviction. That means the first element which is stored is always evicted. That means the element stored in the first row will be evicted and stored in the data center. After this, all the indexes will be decremented. That is, the data which is stored in second will come to position 1, the data which is stored in position 1 will come to position 0, and the new value, which is the incoming data, will be stored in the last position. This way the first in first out algorithm works. Results for the given test sets can be explained or analyzed using the waveforms. This is the output of test set 1. Here we can see that 3 requests are coming in the end. This signal gives us if it is a send or a request. It goes high means it is a request. Here we can see that device 2 is requesting 1024 bytes with tag 12. Here in the data out we can see device 2 getting 1024 bytes with tag 12, which was initially stored by device 3. Here we can see that it was initially stored by device 3. This is the way the output waveforms can be analyzed. This is the waveform which shows how exactly the output waveform is generated and how does it look.
The latency calculations of our system are as shown in this Excel sheet. In between the client and hub, it is given that the data transfer is serially 5.5 megabits per second. So for 16 bits, it's supposed to be 2912 nanoseconds. Considering the read-write latency for the particular memories and along with the buffer latency, that is 10 nanoseconds, we get the 16-bit latency for memory 1 as 3002 nanoseconds, for memory 2 as 3072 nanoseconds, and memory 3, that is L3, as 3072 nanoseconds. Accordingly, we calculate the latencies for the particular bytes stored in the particular memories L1, L2, L3. Now, if we need to approach the data center, it's a different latency. Between the hub and the data center, it is serially 1200 bits per second. That is, for 16 bits, it's supposed to be 13,333,343 nanoseconds, including the buffer latency, that is 10 nanoseconds, along with the read-write latency of the particular memory, that is L1, L2, L3. We get the total and the one more latency, that is 100 clock seconds between the satellite and the data center, as mentioned into the problem statement. We get the final latency for the particular bytes needed to be evicted from the memory, from the particular memories to the data center. And here are the latencies for the data request, as in if the data is not present inside the memories and we need to approach the data center for getting the data. Here are the latency values that are mentioned. Here are the results for the latency calculations for the particular test sets. As in, for the test set 1, we need to access the data center thrice, and hence the total latency involved is this many clock cycles, and the total communication cost is 0.31 US dollars. For the test set 2, we just have to access the data center thrice, and the total latency involved is these many clock cycles, and the total cost is around 0.004 US dollars, which is negligibly small and can be considered as zero. And for the test set 3, the accessing data center is for 8 times, and the total latency will be these many clock cycles, and the total communication cost for test set 3 will be 0.91 US dollars. So for the sake of total communication that is happening over here, uh, it is the total communication cost turns out to be 1.25 US dollars. Uh, so finally, I can conclude, as you have seen the complete overview of the complete system, I can conclude that our system is pretty affordable and reliable, as we have maintained the proper trade-off in between the cost and the latency. Though the latency is little bit more, but the cost here is really maintained. The memories are optimized, and we have a backup memory option that is available. And our system is more efficient, as there are less transactions that is happening in with the data center. And so I can conclude that this system is saleable. Thank you.